Okay, welcome back everyone. Today we are going to sort of continue our discussion on exact differential equations, but now we're kind of going to generalize the concept of exact differential equations, and that is by if we have an equation that looks like an exact differential equation, but does not satisfy that important property that I'll remind ourselves of again here in a second, we can actually make it satisfy that property by multiplying by some integrating factor. So that should be reminiscent of what we've done in the past with integrating factors, which kind of allowed us to do connect product rule in that case. It's a bit different here though, as we shall see. So the idea here is that we have, let's look at an equation of the form of an exact differential equation, right? But in this case, it does not satisfy this special property, and that is that the partial derivative of a with respect to y is not equal to the partial derivative of b with respect to x. Okay. And so the question here is, can we find some function often called mu of x, often used to denote it with mu, two variable function mu, such that mu times a plus mu times b, so those two functions instead, form an exact differential equation. Okay? So it turns out that this question is a bit too hard to answer. And so what we are going to do is we're going to analyze mu of a single variable. Now it doesn't really matter which variable you use. They're pretty much equivalent. We can pretty much approach it with equivalent strategies for either variable, but without loss of generality, let's just go with x. Okay? Although you will receive slightly different results with y, so maybe that's kind of abusive to say, but I'll just go with x for now. So instead, find mu of x. So that is, i.e., well, if it satisfies this, then we need it to satisfy, if this is an exact differential equation, I should have specified exact, I should have specified that. So such that this is an exact differential equation, right? i.e. it satisfies this property. Well, not that property, right? So in other words, we have, I'll write it like this, mu times a, so take the partial derivative with respect to y of that, is equal to mu times b, partial derivative with respect to x. Nice. Okay, well, what do we have here? Looks like here we don't need product rule because this is a constant, and when we're deriving with respect to y, differentiating. So in other words, this left-hand side is just going to become mu of x times a sub y, and that's equal to, well, here we have to use product rule because both of them are a function of x. Should have specified this. We have, since this is just a single variable of x with respect to x, it's mu prime of x. We're differentiating that term, and then this term stays fixed, plus mu of x, hopefully you can see that, times b sub x, right? That's what we have. So now the idea is that we want to make this sort of a separable differential equation, right? So recall that what we usually do with those is that we want to combine all of the factors of u on one side in this, right? So although this is kind of reminiscent of a separable differential equation, it's slightly different. But it turns out that if we combine all of these mu's and mu primes on one side, we'll get this really nice opportunity to integrate both sides. And we get a nice integrand, i.e. So what do we have? Let's just simplify this a bit. If we gather all the mu's on one side temporarily, and then we can factor out the mu and divide. Well, let's take this one step at a time, but that's the idea. Let's subtract this term on both sides. That will give us mu, and I'll skip a step by factoring out a mu of x out of both terms, times a sub y minus b sub x is equal to mu prime of x times b. Okay, nice. So now let's collect this term on this side by dividing, and then let's move this term with a and b on that side. So all in all, let you guys do the algebra, we'll get mu prime, or maybe the other way around would be better actually, mu prime of x over mu of x. Should have stated the opposite. We should divide this term on both sides and divide b on both sides. Okay, that's equal to, and as you already notice, this looks like a nice, if we integrate that looks like a nice natural log of the denominator here by using a quick u substitution. But we'll get to that in a second. There are some details that we need to consider. So this is just a sub y minus b sub x over b. So before we carelessly integrate both sides, we need to make, there's a small thing to discuss here, and that is that we're integrating with respect to x, right? But that doesn't really make much sense if this term here is not only a function of x. That is the important property here that this must satisfy in order for this method to work, is that this must be solely a func of x. Okay? And again, that's because if we integrated both sides, it wouldn't make much sense. Okay? So what do we have? Let's see. So if we integrate both sides, I'll let you guys do the u substitution on this left-hand side. We're going to get natural log of mu of x. Now we should use absolute value, but I'll argue why we don't here in a second. Because normally you would add the absolute value if you're going to consider constant, but here we're not going to consider any constant. And the reason being, well, first I'll write this out. So this is just going to be a sub y minus b sub x over b. We can't exactly integrate that, so that will take some work to do. And indeed, I guess a better argument here is that, well, we can technically integrate this with respect to x, but this is being set equal to a function of solely x. So that is actually the real reason, the main reason why this needs to be solely a function of x. Anyway, let's continue here. So we're being a bit careless in getting rid of the constant, but that's because, well, if we just solve for mu here in a second, we're just going to keep ending up with a constant on the outside. So this absolute value still becomes a new constant, since we're literally varying over all real numbers. Okay, so mu of x equals, and so what that means is that, well, recall what we're doing here. We're not really looking for a solutions yet. We're just developing a tool to find our solutions. Okay, so when we're multiplying this on both sides, the constant really doesn't matter. We can just divide that out anyway. That's not going to impact our result. So in other words, we might as well assume that our constant is just 1 here. So in other words, we're taking one solution out of the family solutions for our function mu. So this is the important formula that we must remember. So how do we continue here? Well, now we showed that given some sort of selective conditions, we can multiply by mu of x on both sides in order to form a new exact differential equation, which we can solve in the normal way. So maybe I'll clear the board, and we'll take a look at a nice little example of exact differential equations and integrating factors. Okay, let's take a look at our example. Well, recall that what we really want to begin with is to check that, well, this is not an exact differential equation on its own with these values of a's and b's, right? I'll let you guys do that. It's a really quick calculation. Just check that if you take the partial derivative with respect to y of this term, it's not equal to the partial derivative with respect to x of this term. Okay, so after we check that, well, let's try to form an integrating factor. And recall from our previous work, in order to do that, it must hold that this function here has to be solely a function of x. So let's check that. So let's check. Now we can use this method of an integrating factors. Well, what is a sub y? A sub y is just going to be, in fact, we're actually at this simultaneously checking that our condition doesn't hold. So in reality, that step is unnecessary. This directly does it for you. If this is equal to 0, that's going to be because the numerator is equal to 0, and so we're just going to get a 0 in general, right? That is that a sub y equals b sub x. Anyway, let's continue. So I'll just write it out then. A sub y equals 3x plus 2y, okay? And b sub x is equal to 2x plus y. Indeed, they're not equal to each other. They vary by this factor of x plus y, and in fact, we'll probably be using that, but we'll see. We'll see here. And now that means that a sub y minus b sub x. Again, I'm kind of loosely using the term a sub y to represent, for example, the partial derivative of y with respect to y, because it's such a mouthful, right? So let's see, what is this going to be equal to? Well, a sub y minus b sub x, as we highlighted, that's going to be a plus x, right? If we take out a factor of x plus y here, divided y. Well, what's b? B is nothing but, let's go back to b, this term here. So that's going to be, if we factor out an x times x plus y. So we can nicely cancel out cancel out this term which contained the y, and we'll be left with 1 over x. So nice. That mean, what have we done then? Well, we've shown that this function is solely a function of x, and now we're free to integrate it and use our integrating factor. So that means that mu of x is equal to e to the integral 1 over x dx, but notice that that's just natural log of x. Again, we needn't worry about this absolute value. It'll create an extra constant anyway, so we don't really need to worry about it. Okay, actually what it'll do is it'll actually create a constant. Okay, let's see what this gives us. So if we multiply, now what we want to do is we want to multiply both sides by x, because, well, e to the natural log of x, those are inverses. The exponential function is bijective, so its inverse is bijective. Anyway, let's see. So if we multiply both sides of this equation by x, then we're gonna get, what do we get? Let's see. So I'll rewrite our a's and b's. 3x squared y plus x y squared plus x cubed plus x squared y. So I kind of just distributed everything. Equals 0. And so you should probably check that this is indeed exact, but by our construction this has to be exact if we did all our calculations correctly. So I'll let you check that. So now what we want to do is we want to find so our goal, find f. Now we're kind of just solving a normal exact differential equation, which we've already done, such that, so I'm going to let this be a, this be b. Should have done that before. but this is our new a and b, right? So find f such that, let's just say f sub x is equal to a, and f sub y is equal to b, i.e. the potential function for the vector field AB. We covered that in a previous video. Okay, so let's just use our strategy highlighted in the previous video to do this. Alright, so we'll have f sub x equals 3x squared plus 3x squared y plus x y squared. So that means that f is equal to, I'll just highlight f of x, y is equal to, now we're integrating with respect to x, so we're going to have that 3 cancels out with 1/3, so x cubed y plus 1/2 x squared y squared plus some function of y. So looping that back in and taking the partial derivative with respect to y, and we'll use this equation, then we form the following equation. Well, a partial derivative with respect to y, we'll get the following: x cubed plus that 2 cancels, so x squared y plus k prime of y is equal to, and indeed it's just this expression right here. So x cubed plus x squared y, we cancel that out, namely that implies that k prime of y is equal to 0, which implies that k of y is some constant, right? And again, as we discussed in a previous video, this constant, we needn't worry about it, because once we actually plug that back in and then use our general formula for the implicit solutions of an exact differential equation, we can just subtract the constant off to create another constant, so we might as well assume that this is 0. So that lost generality, okay? Nice. So what do we have then? So solve. We're just going to have the following. That's just after we plug that value into f of x, which is over here, then we're just going to get this. So we're going to get f of xy equals x cubed y squared, not y squared, plus 1/2 x squared y squared, which is equal to c. So that is our family of solutions. So that was kind of also a nice review of just solving exact differential equations, but also combining what we learned about integrating factors, how they related to exact differential equations. So I hope you enjoyed this video. An upcoming video is actually going to be discussing some real analysis concepts, since that's gotten me going. So I'll see you in those videos. Bye bye.